Lorentz force. So, students, today we will study about the Lorentz force, and this force is defined as the force experienced by a charge when placed at a point where both electric and magnetic field exist. I mean to say that suppose a charge is moving, okay, like there is a charge q, and if this at this point magnetic field and electric field both exist, then both these field will exert a force on this charge, and that is why the total force is given by the sum of these two forces. So I will write about the Lorentz force. It is the force experienced by a charge placed at a point where both electric and magnetic field exist. When the charge is in, or we can write force experienced by charge when placed in electric field is given as F is equals to Q times electric field. So this is the force experienced by the charge when placed in electric field, and force on charge in magnetic field is F is equals to Q into E cross B. So this is the force of magnetic and force of electric. So total force, therefore, total force on the charge, which is called the Lorentz force, is given by F is equals to Fe plus Fb. That is, we have to add both forces here. This F will be Q times E plus Q times V cross B. The Q is taken common, left with E plus V cross B. So this is the Lorentz force. Now the next topic is expression expression of force acting on a current carrying conductor placed in a uniform magnetic field. So we have to take a conductor, and we generally placed the conductor in the magnetic field, and then we will see how much the force is acting on that current carrying conductor. So let us make a current carrying conductor is here. This is your magnetic field. is a conductor. Okay, this conductor is having a length L. L is the length, and I'm talking about the length, those length which is inside the field. You can take the conductor as like this also. Suppose there is another magnetic field, same value, and now conductor is placed like this. So whenever the condition will be given like that, then you have to take only that length which is inside the field. Okay, so but here we have taken just for the convenience inside the field. Okay, now that electron is moving in this direction, electron, so current will have a direction I, like this. So I will write some assumptions here. Consider a conductor, not conductor only, current carrying conductor placed in a uniform magnetic field. Okay, let B is equals to magnetic field is there. Okay, I is equals to current in the conductor. We will just assume all this data. L is equals to length of conductor within field. A is equals to area of cross section. Okay, and E is equals to charge on one electron, as you know already about this. Small n is equals to number of electrons per unit volume. Vd is equals to, what is Vd? You have studied in chapter number 3, drift velocity. So these are the data. Okay, so force is acting on this, and this force is because of the motion of you have studied a formula, a very famous formula, force is equals to q v sine theta. Okay, you have studied that. So what is q? So q is the charge. If a charge is moving in a magnetic field, so it will experience a force. Okay, but here the conductor is feeling the force. Conductor is experiencing the force. Why? Because conductor is made up of electrons. There is a free electron inside the conductor. That is why. So conductor is given here. If electron is the if you consider the electron as a charge, and you have to consider it. So due to the charge here, we have a force. So if I replace with E, that is a charge on electron, so this Vt, this V is the velocity in general case, but here we will consider the Vd because the electron is having the drift velocity. B, you know that what is B, and this is sine theta. Okay, so this is the force on a single charge. So I will write here, therefore force on an electron due to magnetic field. So this force is given by, according to this, EVT B sine theta. Okay, this is the force on a single charge. But how many charges? But we have to calculate the total force on the conductor. Means on the conductor means on all the electrons. So therefore total force on conductor is equals to total force on all electrons. Means I have to calculate the total number of electrons. So therefore if I consider this force, this F as the total force on conductor, which is must be equals to total force on the electrons is equals to, we can write force on one electron multiplied by total number of electrons. Okay, how can we calculate force on one electron? We have already calculated here. This is equation number 1. Let it be E Vd B sin theta. Okay, and we have to calculate total number of electrons. How can we calculate? So number of electrons can be write like this: number of electrons per unit volume multiplied by volume. This is equals to, so we have calculated the force on one electron, number of electrons per unit volume multiplied by volume. Okay, so E V d B sin theta multiplied by number of electrons per unit volume. We have assumed it as n multiplied by volume. Volume is equals to area into length. So we have F is equals to, you can see from here can we write N E A V D together? You will ask why, but let me write first. So I will write N E A V D. Many of you understand why I am writing this. And B first. So F is equals to B R into this into L we have. Okay. We have used E V D B N L A. Okay. So we have only left with sin theta. So I will write here sin theta. Now what is NEAVD? So you have studied in chapter number 3, NEAVD is equals to I. What is I? Using the relation NEAVD. So this will become BIL sin theta, and this is the final derivation. Force acting on a conductor is equals to BIL sin theta. Now we will see the force between two parallel current carrying conductor. Okay, so for this, let us consider there is a conductor carrying current I1. Okay, and there is another conductor here carrying current I2. Now here both are carrying current in the same direction, and they both will represent create a magnetic field around itself. But here we will consider one by one. That is, let me create the magnetic field of this. I mean to say that I am showing here the magnetic field due to this conductor, and this another conductor is just lying in its field. Okay. In the next diagram, I will produce the magnetic field of this second conductor. Let me draw it. Okay. This is x1, y1. This is x2, y2. And here we have taken x1, y1, this is carrying a current I2, this is carrying a current I1. Now this is the magnetic field created by the current I1, and this magnetic field I will call as B1, and this magnetic field I will call as B2. So this, due to this B2, means due to this magnetic field, okay, so distance I am taking as R, okay, here the magnetic field is in this direction, you can find it with the right hand thumb rule. Magnetic field here will be in this direction. So here tangential magnetic field, this is the magnetic field B2. B2 magnetic field, this is the magnetic field produced by the current I2 when passing through X2, Y2. Okay. Similarly, and this, there is a force in this direction. This is the force. Okay. And this force, this I will take as F1, because this is force acting on this, and this is, I will draw it from here, it will be better. Similarly, here the magnetic field is tangential B1. This is the magnetic field due to the current I1 now, so I am writing B1, and this is the current force acting on 2, and this is the current I2. So I will first calculate this F1 per unit length force. So, but we have B1 is equals to, we have studied mu naught by 4 pi, but we have studied 2. This B1 is due to the current I1 divided by R, and B2 we have mu naught by 4 pi to I2 by R. Okay, so we have the value of magnetic field. If we have to calculate the force first, F1. Force first means the force acting on first conductor. So I will write force acting on conductor X1 Y1 per unit length So this force acting on conductor X1 Y1. So X1 Y1, this is the force. So this X1 Y1 पे जो force लग रहा है वो क्या है? F1. Okay. So this I will call this, and this force is due to the magnetic field of B2. So what is the formula of force? We have studied BIL, sin theta, so 90 degrees taken here because tangential 90 degree you will take. So this is the force on 1, but this force is due to the 2, and this is the current I1, because here the current is I1, force F1 that is acting on this X1 Y1, and this force is because of this B2. So I will write B2 I1, and this is per unit length. Per unit length means L is 1 meter. Okay, so no need to write meter. So F1 is equals to, what is B2? So B2 we have here, I just multiply by I. So I just multiply with I, so mu naught by 4 pi to I1 I2 upon R. Similarly, F2 is equals to, means force acting on conductor X2 Y2. Similarly, V1 I2 multiplied by 1 per meter we are calculating. So this will be mu naught by 4 pi to I1 I2 divided by R. So what we have studied that F1 and F2 being equal. So generalizing, therefore we can write force acting between two parallel conductor is always equals to the carrying current I1 and I2 is equals to 2I1 I2 divided by distance between them. This is the final derivation. So here one important point is there. This force is attractive. Why? Because current is in same direction. If the current is in opposite direction, then force will be of repulsive nature. Now, one important point is there. Definition of 1 ampere. Now 1 ampere is defined from this point. Uh, Initially you have studied that 1 ampere is equals to when coulomb charge when passes in 1 second, then we call it 1 ampere. No, 1 ampere is defined from this point. So let I1 is equals to I2 is equals to 1 ampere. Then force is equals to, what will be the force between two conductors? If these both conductors carrying current 1 ampere each, then F is going to be mu naught by 4 pi into 2 divided by R. So let R is equals to also 1 meter. Both conductors are kept at 1 meter. So it becomes 2 into 1 divided by 1. 2 into 1 by 1, that is equals to 2 only. So what is the value of mu naught? Mu naught has a value 4 pi into 10 to power minus 7 into 2 and divided by 4 pi. 4 pi cancel, so force is equals to 2 into 10 to power minus 7 Newton. So this is the definition of 1 ampere. What is the definition? If 1 ampere current is passing through two conductors kept parallel to each other at a distance of 1 meter, then they will experience, each conductor will experience a force of 2 into 10 to the power minus 7 Newton. So this is the definition of 1 Newton. You can see in the notes what is written, all the data is given there, and the definition is also written there. Okay, thank you.